Hi everyone, this video is going to look at section 1.5 kinetics of A-level chemistry, looking at an introduction to kinetics, specifically talking about AQA, but relevant for all exam boards. So here's the specification section for 1.5 kinetics. You will see that there is a required practical that needs to be considered. And this does continue very much from GCSE. A lot of the content is GCSE content. There's a little bit of new stuff looking at Maxwell-Boltzmann curves and Maxwell-Boltzmann distribution just here, but the majority of this is very, very similar to the GCSE content. So the most important thing to think about first of all is collision theory. So have a think back to GCSE. And what do you understand about the term collision theory? What does that mean? Well, most importantly, collision theory is about the fact that reactions don't just happen. If you put reagent A and reagent B in a beaker together, they won't necessarily react. In order for a reaction to occur, the reactant particles have to collide. And it's not actually just as simple as a collision occurring. These collisions have to be of a sufficient energy in order to be successful, and by that we mean for the reaction to actually take place. Now, reactant particles can collide without reactions actually occurring as well. Now, the energy that they need is called the activation energy, written as EA, capital E, subscript capital A. And if a collision isn't hard enough and doesn't exceed the activation energy, then a reaction won't take place. So I've got here just a little animation showing A and B colliding together with energy, forming a product. Now it's actually a little bit more complicated than just reacting together with enough energy. You also have to have the reactants in the correct orientation, and that means the right way round. If you've got a reactant molecule with an X functional group at the end that is going to react together with a Y functional group on another one, if this end of the molecule was to collide with this end, then you wouldn't get a reaction. You would actually have to have X and Y, that bit of the molecule coming together to cause a reaction to occur. So it's about energy and also orientation. So we think back to GCSE, we had a definition for rate of reaction. And you might remember that it's the amount of product produced in a given amount of time, or the amount of reactant used in a given amount of time. Now, unfortunately, that isn't actually the definition we want at A-level. There is a different definition which does actually come up at GCSE as well. But accepted at A-level only is that the rate of a chemical reaction is the change in concentration per unit time. Now that can be the concentration of the product or the reactant, but that's what we talk about, change in concentration per unit time. Now I'll put that in yellow because it is a definition. Now in terms of units, because we're talking about concentration, at A-level, concentration is measured in moles per decimeter cubed, and time would be in seconds. So the unit of rate is moles per decimeter cubed per second. Now I mentioned activation energy already, and there is a definition for that, and luckily it is the same definition as for GCSE. Can you think back to GCSE and remember that definition? Well, if you couldn't remember, the definition is the minimum energy that particles must have when they collide in order for a reaction to take place. Now we can say for a successful reaction instead of for a reaction to take place. Both of those mean the same thing. Now make sure you've got both of those definitions written down in your notes. You must learn them. They can ask them in the exam, and if they do, it's a nice easy one marker if you know the answer. So another little bit of a reminder from GCSE, and this is just something a little bit silly. So we're going to look at Bob. You can see Bob on his bike there. And if Bob doesn't eat a decent breakfast, he's not going to have enough energy to be able to ride his bike over the hill from his house to school. He won't be able to get over that crest of that hill, and he'll just end up back where he started. You can see he looks a bit sad there. He's not able to get to school, as I'm sure you're all feeling right now. Now we can use this analogy or model to help explain activation energy, or EA, in the form of a graph. Where Bob starts is the reactants, and school that he's trying to get to would be the products of the reaction. So we've got the starting and finishing points of our chemical reaction. And that bump that's got to be overcome represents the activation energy. So we can write this as a graph. Okay, I put energy on the y-axis and I've put progress of reaction on the x, although to be perfectly honest, you don't need an x-axis on this at all because it is just a sketch graph. So you sometimes find that there's no x-axis on diagrams of these. And this is known as a reaction profile. Okay, it shows us just the energy changes occurring in a chemical reaction. And it's a really basic graph. Now, the difference in energy between the energy of the reactants and the bump that needs to be overcome represents the value of the activation energy. And that's really important for you to know. So make sure you've got that sketched in your notes with labels before you carry on. So moving on to looking at controlling rate of chemical reaction. Being able to control reaction rate is very useful. Can you think of any reasons why? Well, first of all, the most important reason for being able to increase rate of reaction is to make products more quickly, for example, to make more money. If you own a factory and you're wanting to sell a product and make money, you need to make your product quickly, so increasing the rate of production would be very handy. Now we might want to increase the rate of chemical reaction to get rid of reactants faster. So for example, getting rid of pollutants. We might want to get rid of pollution coming out of a car or out of a factory chimney. So we might want to increase chemical reaction rate to decompose reactants faster. On the other hand, we might want to decrease rate of reaction, for example, to stop things going mouldy. That's why we put things in a fridge. It slows down the chemical reactions that causes mould to form. So by controlling the collisions in a reaction, we can either speed up or slow down that reaction rate. So thinking about changing rate of reaction, increasing the rate of a chemical reaction is fairly easy. And there are two things that we can do. We either increase the frequency of the collisions, and that means having more collisions in a particular time, or we increase the energy of the collisions so that more of them meet or exceed activation energy. Now we can do both of those at the same time. Ordinarily we'd do one or the other. Now the term frequency here, that is really important. We'd never want to say more collisions. Okay, frequency of collisions is extremely important just to bear in mind as a key term. So there are 4 factors that affect rate of reaction that you need to be aware of. Temperature is the main one. So heating up a substance gives the particles more kinetic energy, which means they move faster and will therefore collide more frequently and with a higher energy. And this causes more frequent successful collisions and therefore a higher rate of reaction. Now, a little fact to be aware of at AS level or year 1 of A level is that if you start at standard conditions, that means 298 Kelvin and standard pressure. If you increase the temperature from 298 kelvins or 25 degrees C by 10 degrees C, you get an approximate doubling of rate of reaction. So that's just something nice to be aware of. From standard conditions, if you increase by 10 degrees C, you get a doubling of the rate of reaction. Now the next thing to look about is concentration and pressure. Now they come under the same heading here, because both of them are a measure of the number of particles in a particular volume. Concentration is the number of particles in a volume of solution, and pressure is a count of the number of particles in a volume of gas. So they both affect rate of reaction in the same way. As I've already said, both are a measure of particles in a given volume. If there are more particles in the space, you get more frequent successful collisions and therefore a higher rate of reaction. It's that simple. Now for both of these, you might notice that we've got the term more frequent successful collisions highlighted in bold, and that's because it is very important to be aware of that term. The next one to consider is surface area. Only the outside surface of a solid reactant is able to react. It's a bit like if you put a jacket potato in the oven. It cooks from the outside in. The heat energy has to conduct from the outside and move inwards to cook the inside of the potato last. So if we cut up the reactant into smaller pieces, this will allow a larger surface area for collisions between the reactants. If we were to cut up a potato into chips, it would cook quicker because the heat can get to the inside because you've cut it up. So more frequent successful collisions results in a higher rate of reaction. I've got a little bit of a diagram here just showing that. We have a low surface area on the left-hand side because we have this large lump. And if we take the same mass and cut it in half, we're opening up the inside of that block. So we've got these two extra surfaces that are able to react. And on the right-hand side, we've cut them in half again. And so we've got this extra inside surface that the other particles can react with. So those are the 3 or 4, if you count concentration and pressure as 2 separate things, main areas that you need to be really aware of. Pause the video and make sure you've made some notes on that, paying particular attention to the bits in bold. They are particularly important. Now the fourth area, the fourth factor that affects rate of reaction is the use of a catalyst. Now catalysts work by providing an alternative reaction route, such as a surface for the reactants to react on. Now if we look at that in more detail, gases move randomly in all directions in 3 dimensions, so the chances of a collision between gas particles are very low. And I've got here this representation, obviously on a screen where you can only show 2 dimensions, so you've got to imagine that they're going around in all 3 dimensions backwards and forwards as well. Now this random movement means that these collisions are really unlikely. So if we provide a surface for the gases to adsorb to, now adsorb means stick if you think about adhesive, so we're adsorbing the gases to a surface, this means that they're only moving in one plane and are more likely to collide. And what I mean by that is if you imagine snooker or pool balls on a table, those balls are moving around in the plane of that table and they can move in any direction, but they're stuck to that plane. They can't move up or down. So here's the surface, and if we put our reactant particles in here, they can now only move along that surface. And that means that they're more likely to collide. We've just taken away some of the random movement. Now what this does, this is a way of lowering the activation energy of the reaction, and this therefore increases rate of reaction. And as we said already, an increased rate of reaction means more product and more money. So catalysts are a very common thing to use in industry, in factories and stuff like that, to just increase rate of reaction. Now catalytic converters are something that people need to be aware of. This comes up in the alkanes part of organic chemistry. And catalytic converters in cars break harmful gases such as carbon monoxide and nitrogen oxides into less harmful gases. I'm not going to go through the equations for that now, but you do need to know the equations, so check on your alkanes work. Now the converter breaks down the carbon monoxide and nitrogen oxides by using a platinum mesh. The gas particles would not have much chance of colliding when whizzing around randomly. However, they are able to stick or adsorb onto the mesh. This means that they're whizzing around in one direction only and are therefore more likely to collide. Now, although platinum is really expensive, it's used as the catalyst, doesn't get used up in the reaction. So although it wears away over a long period of time, the catalyst itself doesn't get used. And that's something that people might remember from GCSE. Catalysts can be used in a chemical reaction because they do not get used up in the chemical reaction. Here's a picture of a catalytic converter just to make the slide a bit more interesting. Now to look at the alternative reaction routes in a little bit more detail, we can also take catalysts as part of a staged procedure rather than a catalyst being a surface that we stick our gases to. Catalysts can also just be a chemical that gets used and then produced at the end. So if we were to look at this reaction, A plus B forming C, that might be very, very slow. And it could be quicker to go via a staged mechanism. For example, A plus X forming Y, and then B from our original reaction reacting with Y to make C and X. those two stages might be much quicker than A plus B forming C directly. Although, as I've put here in green, stage processes do almost always result in a lower yield. So you would get a faster reaction but less of your product at the end. It'd be very much a balance between how quick you need your product and how much you want. Now what we can see here is that X is used in stage 1, just here where we do A plus X, but then it's regenerated or reproduced in stage 2. So X is therefore a catalyst because it increases the rate of the reaction. It makes this a faster process, but it's unchanged at the end of the process. So platinum mesh in a catalytic converter doesn't actually react and wear away. It is the same at the end as it is at the beginning. And X in this case is a catalyst because it is used but regenerated. It remains unchanged chemically at the end. Can you think of any other examples of this from Year 1 A-level chemistry that you've looked at already? Have a think. So the alternative reaction route example I was thinking of is free radical substitution mechanism for the decomposition of ozone. So this is something that you have already looked at. This is in halogen alkanes. And it is all about chlorine radicals, which we can just see here, Cl dot. Now chlorine radicals are actually just chlorine atoms. If we were to look at a chlorine atom has 7 outer shell electrons, so it has this unpaired electron just here. Now that's all a radical is. A radical is something that has an unpaired electron. You don't need to worry about, that it's not anything different. Literally it is the same thing. Chlorine radical, chlorine atom, same thing. Anyway, that chlorine radical can react with ozone, forming a ClO dot radical and an oxygen molecule. Now that ClO dot is extremely reactive and can therefore react with more of the ozone molecules, okay, breaking more ozone down into oxygen molecules and reforming that ClO dot. So what we've got here is the chlorine radical being used in the first reaction and regenerated in the second. And so therefore the chlorine radical Cl dot is a catalyst for the process as it's regenerated at the end. And this is commonly asked at A level. Now what we can see is overall, if we look at this reaction, we've got Cl dot on both sides of the reaction, left on the top and right on the bottom. And then we have the ClO dot on the right on the top and left at the bottom. Overall, on the left, we have 2 ozone molecules, and on the right, we have 3 oxygen molecules. And so overall, the chlorine is catalyzing this reaction where 2 ozone molecules form 3 oxygens, and that's how ozone breaks down. This is why one chlorine radical can decompose many, many ozone molecules, because the chlorine radical can just keep doing that over and over and over again. Now, when it comes to adding a catalyst, we need to think about how this affects the reaction profile. Now, again, we don't need that x-axis on the bottom, but it often makes people uncomfortable to have a graph with only a y-axis, so I'm going to put it in there. So if we start here with the reactants on the left, forming the products on the right. Now, in the energetics topic, you have to be aware of whether or not this is endothermic or exothermic. You might remember that from GCSE. Now, if we put in the bump there for this chemical reaction, if we add a catalyst, what happens is the activation energy lowers. And so I've shown here in pink, with this pink dotted line, the addition of a catalyst. Now what we can see is that we have a lower activation energy. The amount of energy to go from the reactants to the top of the bump is lower now that we've added a catalyst. And as we've already said, if the activation energy is lower, then more of the particle collisions will be successful, and the rate of reaction will increase. Make sure you've got that diagram. It is really important, but as I've said already, remember that the activation energy is actually from the top of the bump, or from the level with the reactants to the top of that bump. Now, just to finish off with a few examples of using catalysts from GCSE. So, cracking long hydrocarbons into shorter alkanes and alkenes using porcelain pot or alumina, obviously comes up at A-level as well. The production of ethanol from steam and ethene. Hydrogenation of alkenes, which means adding hydrogen, breaking the double bonds and forming alkanes. That's with a nickel catalyst and takes place at around 60 degrees C. Buckyballs. You looked at buckyballs at GCSE as an allotrope of carbon, and one of their uses is as a catalyst in chemical reactions. The differences between low-density polyethene, that's LDPE, and high-density polyethene, HDPE, are due to different catalysts during production. High-density polyethene is formed by adding a catalyst enabling straight chain polymers to be formed, which means that they can get very close together, they're more dense. A use of nanoscience or nanotechnology could be to find new catalysts for chemical reactions. And hydrogen peroxide can be decomposed more quickly using manganese oxide, potato, or even liver or blood. Now, some of those will come up at A-level, others are just interesting to know about. All of them could be used as possible frameworks for questions at A-level, where they give you information in the stem of a question. So, if you've got any questions about anything in this video, do let me know, get in contact. Go back over it, make sure you've got the key terms, especially the things in bold, and remember the definitions.